Okay, let's start this problem. One use of exponential growth and where it can be applied is when you're looking at the value of how a classic car behaves over time. So let's take this hypothetical Ferrari, and at any given point in time, which we're going to call time 0, it grows at a rate of 10% each year. So if the car's starting worth is $100,000 at time 0, its worth in one more year will be that $100,000 plus 10%. So the way you would find 10% is take 100,000, multiply it by 0.1, which is the decimal form of 10%. That gives you 10,000, and then you have to add those together. Another way of arriving at the new value is to multiply 100,000 by 1.10, which gives the original value plus another 10%. Each year, the value is going to be multiplied by 1.10, so it becomes a common ratio situation. So that's where we're tying it back to this guy right here. Because we're multiplying by the same number, the pattern that fits that scenario is a geometric sequence. So another word for geometric sequence can be exponential growth. It can also be decay, but we're focusing on growth in this lesson right here. Okay? So this says complete the table of values for the Ferrari, giving a growth rate of 10% each year. So the original amount is 100,000. Our table right here doesn't have the odd years, so we're going to fill them in just so that we're clear. So 1, 3, 5, 7, 9, trying to 1, 3, 5, 7. Oh, I made that number a little too close. 11, 13. We can stop there. That looks about right, what we'll need. Okay, so if I want to go from 100,000 to figure out what it's going to be worth, if I just do 100,000 times 0.1, which is the 10%, that would give me $10,000. So then right here, I would write $10,000, but that doesn't make sense because it started off at 100,000 and then it would be 10,000. So what it actually is that 100,000 plus that $10,000. We could keep doing that, going times 0.1 and then adding those two numbers together to get the next value. But what you'll realize is what you're doing is saying keep the 100% original value, but then add 10%. So that would be 110%. Well, what's 110% as a decimal? Here's the decimal place, move it over, 1.10. So what we can do is instead take 100,000, and then what we're going to do is multiply it by 1.10. So there we get the $110,000 that it's worth. So I'm going to put that here. Now, like we said, this is geometric and representing exponential growth. So if I just times it by 1.1, I'll get the next value. That's 121,000. Okay, and then multiply that by 1.1 to get the next value. This should look familiar. And so on and so forth. So I can keep using my calculator to do it. I've actually already done it. So I'm just going to go ahead and fill these out for you guys. And you're knowing that I just multiplied the previous one by 1.1 to get the next one. Is the silence awkward for you? It's awkward for me. Good thing I'm almost done. Ooh, I think I wrote that down. There's no 3 right there. Alrighty, we finished filling out that table. So now we're going to go ahead and graph it real quick. So let's do that. So at 0, which is that number right there, it's equal to 100,000. Okay. And you could graph all of those 14 years plus year 0 would make 15 years, but I'm just going to graph the evens. So this one's 121. I'm just going to be careful to make sure I graph it where it goes. And then on year 4, it's 146. And then year 8, or year 6, let's go there. Year 6, 177. Year 8, 214. Year 10 is at 260-ish, almost. Year 12 is at 313, and year 14 is at 380. So that's off the graph, but that's okay. So our graph is coming up like that, and from left to right, since we're going up a hill, that's definitely exponential growth. I just want to point out that this graph can continue into the negatives, but in the context of this situation, that doesn't make sense. So you're not going to go backwards in time. So right here, that's why we only have our graph to 0. And when we were graphing these, and they were the nice clean graphs where we were shifting and transforming, there was actually an asymptote here. We don't have to worry about that asymptote in this particular problem. So then we need to write the equation. So the formula we're using for this equation is this guy right here, where that value, see the little knot? That's called a knot right there. It looks like a 0, but that's representing whatever there. It means initial. You might have seen it in science as well. So we're going to write f of x equals 100,000. And then we have a to the x. Well, your a value, I already told you guys, your a value is your common ratio. What number were we multiplying everything by? It's that 1.10, and then raised to the x power. So right here, if it says what's the nth term is the general term, so it's a formula, and this isn't going to fit in here. But this might look familiar to you because we wrote rules for geometric sequences like that. It's just the context on when do I write it with the n and when do I write it with the x. Okay? So moving on, with your calculator, we're actually just going to do it with our brain and using the table. Can you figure out to the nearest year approximately when the value of the car will be double? So to the nearest year, we're looking here, it starts off at 100,000, double would be 200,000. Between year 6 and 8, 100,000 would fit. Over here to the nearest year, year 7, it's almost at 200,000. So we're going to do 7 years. This says, how could you guess and check to get more accurate? You could use the formula that you created, right? So you could plug in 7.1, 7.2, etc. till you get the right value. What about triple? How long does it take for it to triple? So that would be 300,000. So as I'm looking, 300,000, well, 11,000 is 285,000, which is about 15 grand away from 300,000. And year 12 is 313,000, which is 13, almost 14 grand away. So that one's closer. So we'll say year 12 years. Okay. All right. Write the value equation for these different Ferraris that have different initial values and rates of growth than the one we just looked at. Alright, so again, the formula that we use, I'm just going to write it right here, f of x equals the initial amount times the common ratio raised to the x power. So I have the initial amount right here, so I'm writing f of x. Yes, you have to write f of x equals. It says write an equation. If you don't have that, then it's not an equation. So follow the directions. 80,000. And then the a part, what is a going to be? So we have 1 from the 100% because it's not losing that original value plus 0.05. Okay, so this is going to be 1.05 to the x. And I just want to touch up on that real quick. Guys, you know the car is growing in value because it's a classic car. So if I have 80,000 and I just multiply it by 0.05, the next value of the car would be $4,000. That doesn't make sense. A car didn't go from $80,000 to $4,000 when it's supposed to be growing. So again, the reason why we times by 1.04 is because, or 0.5, is because we are saying you retained 100% of your $80,000 and then you gained another 5%, which makes the car $84,000. All right, let's take a look at this one. This one's initial amount, ooh, it's a little bit pricier, $125,000, and man, is that growing. So that's 1 plus 0.12 right there. Okay, so convert this to a decimal and we get 0.12. So our common ratio is 1.12. This one, I think you guys are getting the hang of this. We just have to make sure that we recognize that it's growth, and when you are growing, you are going to be adding that percentage. So 1, 2. Now tomorrow's lesson we're going to be decaying, so you're losing value, but you're going to need to subtract instead of add. So use your calculator to do the math for that, because some of you end up doing some of that wrong. Okay, so the next piece says exponential growth using percents. If a growth rate is given as a percent of the initial amount, convert the percent to a decimal and add 1 to get the common ratio A. Use the initial amount at time 0 for the C sub 0 or C naught. So the average population growth of San Diego has been approximately 5.16% from 650 people in 1850 to 2000. So estimate the population in the following years. So you're like, what the heck? So here's our formula right there. We have y equals, or let's even just do f of x. The initial amount was 650 people, and we're growing. The population's getting bigger. So that's going to be 1 plus, convert that to a decimal, 0.0156, 0.516, raised to the x power. Okay? And then this next thing says, estimate the population in the following years. So here's our formula, and it says 1900. So remember, this initial time was 1850. So we can't just plug 1900 in. We're looking at how many years have gone by. So how many years have gone by from 1850 to 1900? That's 50 years. Let's just do all of these, right? To 1945, we're going to have x equals 95 years. For this one, to 2000, x equals 150 years. And then 2015, we have x equals 165 years. Okay, so you have to be careful with the problems to see what it's calculating, but we're saying time 0 is here. So in 1900, how many years have gone by? So that, like I said before, it was 50 years. I'm adjusting it to be consistent with the other ones. All right, so how do we figure out the population in those years? We just plug into that nice formula we made and use our calculator. So there's that one. So we have 650 times 1.0516 raised to the 50th power. There we go, 8,043, and it says estimate the population. So we'll just round to the whole number. So 8,043. Okay, let's do the next one. So you do need to show your math. You need to defend your answer. So that means you need to write this out. I know what I'm doing. I'm plugging in the 95 in for x. But I can show you a little trick in your calculator. So the formula is the same. The only thing that's different is plugging in that number. So if you hit second and then the enter button right here, you see how it says entry? then that comes up like that. It pulls up your last equation, and I can just scroll and change this to 95. I think you guys even have fancier calculators than me, so you can literally just arrow up and then type over the 50 and put 95. All right, it's growing. So we have 77,396 people. Now, I didn't put my unit on the first one, but I'm going to go back because I want to make sure that I am putting my unit on there because it's an application problem. So f of 150 just going to go into my calculator and type in 150. So, wow, we're getting really big. That makes sense, right? So this is 1,231,686 people. And our very last one, oops, 165 years later. Again, I typed it into my calculator first, but I got to show my work. I have to show what I plugged in where. And I get 2,619,743 people. That's a lot of people. Alrighty, that's it for today.